All right, hello everyone. Welcome back to class. We're off to a bit of a delayed start, but that's okay. So as you probably realize, this is the second class of 8 for the second level. See, someone's talking about their chess set in class, maybe at the end if we have
I've got
time.
2/3 of a chess set done in CAD.
Yeah, we can take a look at that when we take a break in the class. I'd be interested in seeing what you did.
What if you want to play with it? You wouldn't have a king or your ponies. So I don't know how you can play with it.
Well, it's an exercise for the user. Yeah, chess sets are always fun to do since the pieces are pretty abstract. I know last class we went over the rook, so I guess some of you may have had the idea to do the others, which I encourage. As for today, we'll talk a bit about a few new concepts when it comes to CAD and CAD-related engineering in general. So kind of the first new thing that we're doing of the class. Last week was more of a review, kind of getting your exercise back or getting back into practice with Onshape. So now we're going to talk about some things that maybe you didn't know about before, specifically engineering drawings. And I hinted at this last class. I showed the slide, I think, at the end of the last class. And the idea of the engineering drawing is that when you make a 3D model in CAD, such as this one, in general, you don't want the design to end at CAD, right? That is, a lot of the time, the reason that you make models in CAD is so that these things can be brought into real life objects, or maybe someone else can enjoy your model, they can make use of it. But the end goal of most CAD is not just to have this model sitting on your own personal private instance of a CAD application. It's to convey that information to other people. So I guess to start off introducing a drawing, when you think of the word drawing, pardon, when you think of the word drawing, you probably have an idea in your mind, like an artist's drawing, an illustration, like concept art. And so an engineering drawing is a bit different from that. It has a very specific purpose, which is to convey all the information that you need to create a model and no more than that. So it's very efficient, it's very full of information. And in theory and principle, if you gave someone a good engineering drawing, then they should be able to recreate the model completely accurately to the way that the designer intended, just by looking at the information in that piece of paper. So you can see here, as an example, we see different views of the model. So in the top right corner here, we kind of see like that view of what this object might look like. And then it shows you these three projected views, right? The front, the top, and the side. There are also other views, which I'll discuss in a moment. But the other important thing is that it contains the object's dimensions. So it tells you, oh, this distance from here to here, that's 1.5 inches. This is the diameter of this circle, that's however many inches. And so you can see how that's pretty useful, especially for someone who's manufacturing this object, just so that they know that they're making this thing the right size, things like that. So I'll start off by talking about what we mean when we talk about views and view orientations. We have something called the orthographic view, where you're looking at a part from one side. So if you open up your Onshape, which hopefully you have by now, you probably have noticed by now that there's this navigation cube in the top right corner. That's this thing. When you move around your camera, the cube also turns. It gives you your bearings, your coordinates. If you click on top, I'm looking now at the top of my part. If I click on right, I'm looking at the right of my part, and so on. The back, the left, the bottom. So these are our orthographic views. So these are something that we make use of when we try to present drawings, since you have to show multiple views of the object in most cases just to convey the three-dimensional shape on a two-dimensional piece of paper. Another thing that happens when it comes to drawings is people will have conventions for the meaning of various types of lines on their drawing. So when you look at something like this, you'll see not all lines are just like solid black lines. You can see there's solid lines around the edges of this cube, but also I have all these different dashed lines. And what do these mean? The first type is what I'll call a hidden line, which represent the edges of a part that you can't see, but are still there. So a good example of that is a block with a hole in it. And if you just look at the block with the hole in it from the side where there's not a hole. So there's still a hole in the block, but you can't actually see it from the side view, right? The way that you denote that the hole is there is to use these kind of hidden dashed lines. And those just tell the viewer that there's some feature there that you can't see. It's covered up by the geometry of the part that would be there if you look there like in real life. So that's what a hidden line is. I think there'll be some more examples later on, and we'll go through a little exercise together. The next type of line is what we'll call a center line, and that's this line here that goes through the center of this block. So the long dash, short dash, long dash, short dash, that's the center line. And the purpose of these is to indicate symmetry. So if I put one of these lines down, I'm telling you that everything on one side of the line is the same as, it's a mirror image of what's on the other side of that line. It's basically a mirror that you can place right there, and everything on one side is the same as the other. This can be useful in a drawing where you're trying to be efficient with the information you're putting there. Maybe if you put one of these symmetry lines, you don't need to put dimensions on both sides, since the reader can just tell if they know what one side is in dimensions, the other side is exactly the same. So those are center lines. And one more type of line, this one's a bit different, is the break lines. So that's this jagged lightning bolt shaped line here. And that just indicates if you have a really long and continuous uniform object that you're trying to represent, it's often not that useful to draw the entire object. Like maybe it's like a really long flagpole that has a uniform diameter. In that case, you don't want to squeeze the entire flagpole into your tiny letter size sheet of paper. Rather, you can just put a break line in the middle, or put a break line, like one towards the bottom, one towards the top, and just condense it into a smaller form so that it can fit in your drawing. And the reader just assumes they can see the dimension for the total length of the thing. So they just know that you took out some of that stuff in the middle that's redundant. So there we have a few different types of lines. One more thing I'll talk about before we go to the activity is talking about different types of views. And so in a drawing, again, we're trying to represent these three-dimensional objects on a two-dimensional piece of paper. And there's a lot of limitations there. And views, different types of views help us better represent that information on a flat piece of paper. So the classic one is what's called a section view, where you're essentially taking a section, a slice of your object, and then you're presenting to the reader what the inside of that section looks like. So again, if I have my cube with a hole in it, if I take a section through that hole, I can then present the section view, which shows that there is like solid material here. In between, there's a hole, and then there's more solid material here at the other side. There's also something called a detail view, where there might be a lot of fine features localized in a certain area of this part that you're dealing with, and you want to show off those details. They're important for the reader to know about. But if you just included them at the same scale as the rest of the part, they'd be too small to really make use of, or to really see with much detail. And so the detail view just takes a small section, it blows it up to a bigger size, and it puts that view next to it, so the reader can just take a better look at what's there, kind of like a magnifying glass. And the last view I'll discuss is kind of that auxiliary view, which is especially helpful if you're trying to get an idea of what this thing looks like. For example, on this drawing, in the corner here is an auxiliary view that shows what you're looking at from kind of an angle. And that's pretty helpful because if you don't have that and you're just looking at this front, top, and side view, you might be a bit more confused about what this thing really looks like. I know if I just looked at these three views, I'd really have no idea what the 3D part looked like unless I sat down and thought about it for a few minutes. So that auxiliary view is pretty helpful just to help the reader get an idea of what they're dealing with. So that's pretty much all that I'll be really talking about in terms of these drawings. And the main usefulness of this, for the rest of this class, essentially, I'll have you making models based on drawings. And so just getting these ideas in your head, thinking about them. And over time, as you actually start modeling things from drawings, hopefully you'll just be more comfortable and have a better idea of when you'd use drawings to do your own CAD. So we'll move on to a little activity. Again, like last week, I just want you to open your drawing application on your computer or get out a pen and paper, if you will, and take a look at this cylinder with a hole in it. It's kind of like a tube. And if I end up covering this up later, you can always get the slides off of Google Classroom. Make sure to join this. If you're on a Windows computer, you almost certainly have Paint. You can just search for it in your Windows search, or if you're not on a Windows machine, I don't know what the equivalent is, to be honest, for like a Mac, but you can also just get out a piece of paper and a pencil and follow along with the exercise. And so what I want you to do is take a moment just to make sure you understand what this 3D shape is. It's nothing complicated. It's just a tube with a uniform thickness wall. And I'll ask you a few questions about it first. Given the fact that we're trying to represent this 3D object in terms of 2D orthographic views, so like a front view, a top view, a side view, we're trying to represent it with orthographic views. And we also have this other condition that we want to include as little information as you need to fully replicate this geometry. So we don't need to give them too much information. We just want to give them just the right amount of information. So how many views, top, front, back, bottom, left, right, do we need to represent this 3D shape? Just shout out a number, put it in the chat. You can also give me the specific views that you'd want, like top and bottom, or left and right, left and front. But just tell me how many different orthographic views you think you'd need to create a drawing of this shape. All right, first respondent says 2. I'll wait for one more, just so we have a bit of discussion going on. Anyone? All right, no dissension. Everyone agrees that you need 2 views. Yeah, I mean, I'd agree with you there as well. Seems to me that with 2 views that are perpendicular to each other, you kind of get all the information, since if you include more than 2 views, you end up with at least 2 views that are the same as each other, right? Like the front and the back of this tube are going to look exactly the same. Likewise, the top, bottom, left, and right are going to look the same as well, assuming that we're kind of treating the circular face as the front. So good work with that part. Now, if you go back to thinking about the lines, I'd like to ask what lines among these are definitely going to be needed to represent what's happening here. And consider especially what happens when you're looking kind of from the side of this tube. And I don't have a good tube with me right now, but I can use this water bottle kind of to demonstrate. Just imagine that this water bottle is essentially a hollow tube, which it kind of is, right? And if you look from the front view, you definitely know that there's a hole because you can see into the hole, right? But if I'm showing you the other view, the two views that we need, if you're looking at the water bottle kind of from the side, what information are we missing about the geometry, the 3D geometry of this water bottle, if I were just trying to convey it with this 2D image from the side? Like, what about this water bottle can't you see?
The inside.
Right, the inside. And so to kind of convey the fact that there's this something there that you can't see, what kind of lines should we be including in one of our views?
Excuse me.
Yes.
But can you repeat that? I was down there getting a battery for my mouse. It died.
Sure. So we're looking at this tube, which I'll model with this water bottle that I have. Just imagine that this is a cylinder.
Oh, I know how I can do that easily.
Hollow. Right. So so what I'd like you to kind of tell me is like what kind of lines that you'd use if you're trying to make a drawing of this hollow tube. Keeping in mind these different line types that we talked about. Stephen, do you have an answer?
Me?
Yeah.
I did not see the before side. Yeah, I don't.
Or anyone? I will wait to hear an answer before I move on, so we can talk about drawings the entire class. Just speak up if you want to. Yeah.
Excuse me. But
yes.
like, is there a copy and paste?
Yes. I'm not sure exactly what you're trying to do, but there's probably going to be a way to do it. All right, I've yet to hear someone tell me how we're going to solve the problem of how we're going to draw the side of my water bottle, given that you can't see the inside. Maybe Owen, do you have any suggestions? Hidden lines, excellent. So when you do create a drawing of some three-dimensional object like this hollow cylinder, where there's a feature inside that you can't see from the outside, you're going to need to include hidden lines. And so keeping these two facts in mind, the fact that you need two views, two unique views, as well as hidden lines, I want you to kind of create a drawing similar to this one, where you include the two views to fully represent this 3D object, the hollow cylinder. So just pull up your program or your pen and paper, and I just want you to draw those two views, what you think they'll look like. So maybe one of the front, maybe one of the right.
I'm confused.
Right, so all I want you to do right now, pull up your pen and paper or your drawing program, whatever you have, and I want you to create a drawing of this hollow tube. Specifically like an engineering drawing where you're using your orthographic views, you're using your line types to convey all the information that there is to know about this tube, but not any extra information that you don't need. So I'll give you a few minutes to do that, and then we'll come back. Maybe someone can share what they have. So I'll give you just another minute, and then I'll call on a couple people. Just hold up the paper to your camera or share your screen if you use the program. And we can talk about, just try to understand how to make these drawings. And just to give you some background information in general, like you'll be using a CAD program to create these drawings. Onshape has a set of tools that you can use to create drawings like this one. In fact, I created this using Onshape. But we might not get into that specifically in this class, but just know that in general, you don't have to necessarily hand draw all of your drawings. There's ways to kind of get your CAD model into a drawing and working from there. All right, so you've had a couple minutes. First, is there anyone who wants to volunteer to show what they've drawn with the rest of us? And if not, how about Jason? I can stop my screen sharing if you did a program, or you can hold up your paper to your screen, to your camera rather. And don't worry if you're not done either. I just want to get an idea of what you're thinking.
Well, I actually have a prompt when I was using Paint and
Yeah.
then I was bored. So I cropped the pixel size to 10 by 1 pixels, and now I can't get it back.
Pretty unfortunate. Well, I guess I can't ask this of you this time. How about Amy? Would you like to share what you have? Okay, well, that's fair. I won't force you to, but don't be afraid to show, I mean, I guess no need to be afraid since we'll all be supportive of whatever you have, but in that case, how about Christopher?
I don't really have anything. I don't really want to. I don't really want to share. I don't have anything right now.
Can you describe what you think the two views would be? We have agreed, I assume, that there are two views that you'd want.
The views are probably like. I need one view to cover half the ground, the distance, like half the thing, and so the two views need to cover the whole thing. I'd probably make it
Sure.
symmetrical. I think.
Yeah, okay.
Cover the whole thing.
So I think, Jason, you're the one who said two views. You're the first person to say that you need two views. Could you tell us what directions you'd want to view this thing from?
Well, you need view from the side and the top.
All right, that's a great start. So let's go through this together then, since it seems like, you know, we're early in this, we're early in the class. Maybe we're not quite ready to share our artwork with each other. So one from the front, right? So let's call this circular part, like where you're looking straight down into the cylinder. That can be our front view. And so if I look at this tube from the front, what do I see? I see like the circle, the outer diameter of it. And I see another circle, which is kind of the inner diameter, right? And you can imagine this stuff here. Maybe I can fill it in. This is all where the material is, and everything that's white is kind of a hole. There's nothing there. So if I look at this from the front, this is my front view. So what the front of my drawing might look like. And then I need a side view, right? Actually, I'm not going to fill it in, but you can know that this intermediate part is where the material is. And then there's the right view when I'm looking kind of at the side of the cylinder. And when you look at the side of a cylinder, what you really see is a rectangle. So here, I just have something like this for my side view. And as we talked about, when you look at the side of a 3D object with internal features like a hole, there's some information that you can't just see with your eyes, but is still present in the geometry. And that is that hole. If I just showed you this rectangle and you didn't know about this front view, you just knew about the right view, there's nothing to stop you from thinking that it's just a completely filled in solid cylinder. So there needs to be a bit more information than I have here. And the way that I'll achieve that is with some hidden lines. Pardon the poor quality, but just you can imagine that these are nice, pretty dashed lines. And this is something like what the final drawing would look like, where from the front, I see this kind of ring shape, where the middle is kind of this hole. And from the right, all I see is a rectangle when I look at this tube from the right, but I also want to convey this additional information that there's a hole inside using these dashed lines. So I'll pause here, see if you have any questions. I know the drawing concept perhaps is better explained with maybe going between like a 3D model and a drawing, but we're about to do that shortly. So hopefully by the end of this class, you'll have a bit of a better idea. Maybe you can think through these as well on your own. All right, any questions? All right, I'll discard this painting and we'll move on. So as I mentioned in the first class, we're gonna have a series of projects throughout this 8-week class. The first of these is creating this universal joint. And essentially what the universal joint is, it refers to kind of this part in the middle of this assembly here. And what you have is the ability to convert rotation along one direction into rotation along a different angle, a different direction that's at an angle to the first direction. So you can imagine this is pretty useful wherever you have rotating parts like an engine, and you need to convert that rotation from wherever the motor output shaft happens to be to some other shaft that's at a different angle in a different position. And you can use this kind of coupling that connects these shafts so that their rotation, so that they rotate together essentially. I would show you the animation, but I didn't check this before the class, and it turns out for some reason the animation is broken. Something about this assembly is not quite right, but you can imagine this is how it would spin. I will assure you that in practice, this completes the full rotation. And I'm pretty sure that geometrically it also does. There's something about the way that this was assembled just isn't cooperating today. But you can see if I turn it just by hand, just by dragging it, it does kind of spin. So there you go, that's what we're going to be making. And we're going to be making it from a drawing. So our task for this class and next class is hopefully to model and assemble this whole thing that you see before you. I'd suggest you create a new document, title it whatever you want. And what's different of what we're doing today compared to the previous classes that we've done is that everyone is going to have exactly the same 3D model because we're going to follow the exact same drawing. In this case, I'll start off by modeling this part called the clevis. Kind of looks like a fork, like a tuning fork with these holes in the side. And I'm going to kind of demonstrate how you might look at a drawing like this and how you can create a CAD model by looking at this. And so I start by looking at kind of this auxiliary view, this view from the angle up on this corner. And this gives me a pretty good idea just on what this thing looks like three-dimensionally. There's this kind of squared off U shape for like the tines of the fork. There's a hole that goes through the side of this fork towards the tip. And then there's a cylindrical rod that comes out from the center of like the back of that U shape. And so I know what this thing looks like three-dimensionally. I can picture it in my head. And now I go and look at this drawing. And from this drawing, I can begin to think about how I'm going to model this. And like we do before, I start by thinking like, what are the shapes present? What are the features and on-shape I'm going to use? So you can take a moment to think about it in your head, but I'm going to spoil it in a second. I personally see some rectangles here. I see one big rectangle here, another smaller rectangle here. I can maybe extrude out that remaining shape that's kind of like a U shape, and that'll give me kind of the fork part. Then I know that I can maybe extrude these holes from the side and extrude out another rod from the back to finish off this clevis. So now I have a plan, and now I'll execute it. So starting off as we do, we make a sketch. And for this first part, I'll more or less try to go through the whole process with you for, I guess, to the end of this class. And then just to give you an idea, there are 2 more parts, and it'll be an exercise for you to try to model these on your own between this class and next class for homework. So that's that. I said I want a rectangle, so I'll just draw a rectangle as you know how to do. Personally, I like the rectangle to kind of be centered at the origin, I like one side of it to be centered at the origin. So I'll use my midpoint constraint. Just take this point, take this line, and that constraint forces the origin to be the midpoint of this side of the rectangle. So now I have a rectangle that's kind of centered on the x-axis, right? And now how big is this rectangle? The answer is in the drawing. I go back, I take a look, and I see that from here to here, that's 2 inches in the drawing. I see the number 2.000. So I know based on that, that the width of my rectangle, the base, this should be 2 inches. Next question, how tall is this rectangle? It's in the drawing. I go back, I look for it, where is it? I see it here. From here to here, the dimension of this part of the rectangle should be 1.5 inches. So I see that in the drawing. And then I go back to Onshape. I'm going to dimension it from this side. Not that it really matters. To 1.5 inches. And so now everything's fully dimensioned. I'm not done with the sketch yet, but I know that this is accurate to what the drawing tells me that this fork should look like. Now there's just a bit more to do. I do want to kind of get the inside here. And so there's a few ways that I could go about that. I think I'll just draw some lines. So I'll go to my line tool. And again, I can do the thing where if I'm really careful with how I place my cursor before I make my clicks, you can see that Onshape sometimes gives you these assumed constraints where if I hover right here, Onshape assumes that I want a line that's perpendicular, which I do. So before you click, if you kind of hover your mouse in the right place, now you can see that Onshape is assuming that I want a vertical line, which I do. So just make sure I'm hovering in the right place before I click, and that'll just make me a vertical line. So that just saves me some time later on where I don't have to make these constraints manually from this menu. And I'll just make one more. Again, you can see that Onshape can guess what constraints I want. It knows I want it to be coincident with this vertical line as well as parallel to this other line. So thanks to that, there's a lot of the work already done for me where I don't have to create a bunch of constraints to make sure these lines behave. That said, if you can't get that for some reason, you can always just add these constraints on your own. So this line should be vertical using the vertical constraint. This line should be horizontal, and so on. So now I need to know how to dimension these lines. What I do see here is that the distance between the bottom of the fork and the top of this bottom tine, so to speak, of this fork, that distance here, the thickness there is 0.250 inches, a quarter inch. Then I look here and I see this dash line dot, that's a center line. And so that means that everything on the other side is exactly the same, kind of in a mirror fashion. So I know that the thickness here of this one, the distance from this topmost line to the next line down here, is also a quarter inch, or 2.250 inches. So I'll make use of that information. I know the distance from here to here is 0.25. And likewise, I know the distance from here to here is also 0.25. And all of that is just based on the drawing. So I didn't do any thinking, I didn't do any guessing. I just looked at the drawing and the information was there for me to know those dimensions. There's just one more dimension left, and that's the distance from kind of here, the base, of the fork, and here kind of the thickness of that part. And again, I see the distance between those on the drawing is 0.25, a quarter inch. So last thing I need to do is create that dimension from here to here and just mark it off 0.25 inches, and I'm done. Everything's fully defined. If for some reason with these dimensions it's not fully defined, you might be missing some constraints. Make sure this line is horizontal, this line is horizontal, make sure this one is vertical. And if that's the case, I think that's all you need to make this sketch. So from here, the sketch itself, like this isn't anything new to you.
Excuse me, but how did I constrain, like, how did you do the 2.5 to 0.25? I'm confused. How did you do that?
So anytime I have like a number that tells you how long something is or how far apart things are, all of that is done with the same dimension tool. So when in doubt, you start off with the dimension tool when you're trying to make a dimension. And then in this case, there's a few ways that I can go about this. For me, I know the way that I think about it is I'm trying to dimension the thickness of this part here.
But how do
So-
I do it?
Right. So
Can you show me again?
yeah, what I do is I click the tool, I click this first edge here, and then the next thing I click is this other edge here. And Onshape will understand that I want the distance between those two. Another way that I can do it is to do it between points. So I could also have selected this point here and this point here. And that also ends up being the same distance just because those points lie on those lines. In fact, I could also have even done like this point, and still the vertical distance between those is kind of the same geometry. And likewise, for this one, I can just select this line and this line. All right, so from here, next thing to do is to extrude the fork. You all know what to do, but what you might not know is how thick you have to extrude it, how deep you have to make the extrusion. So whenever I have this question, I go back to the drawing and I take a look around. When I think about it, if I call this the top view of the fork, then the depth of the extrusion should be kind of how tall the fork is when you look at it from the side. So I look at the side view, which is this view here, and I see the thickness of this fork here is 0.5 inches, so half an inch. And so I know I want to extrude this part, this U shape, and I know the depth that I want to extrude it is 0.5. And again, that's purely based on drawing, nothing I'm making up here. Any
It's
person,
not working, like it wouldn't hollow.
we can take a look at it maybe at the end of class if we have a moment. For now, since we're
Look
kind
at
of,
my screen because it's being very confusing.
all right, sure, go ahead.
Okay, so wait, what? I can't seem to find Google. Sorry, I can't find it.
Sure. I do want to get through this demonstration or as much of it as I can, so I'll keep going, but towards the end of the class, if we have time, I can take a look at that individually. So just a couple more features left on this clevis, on this fork. The first of which is the rod, the handle that comes out of it. And I'll start with that. So just looking at this auxiliary view, at this angled view, I might not be completely certain what shape this like rod is, but if it's ambiguous, all I have to do is look at this kind of left view. And looking here, looking down onto the rod, I can see that its face, its cross section is a circle. So I know that it's a cylinder just based on that information. And then I need to know the diameter of this cylinder. The way that I can figure that is by looking at the side view. Yes, I'm being ambiguous with names now. I'll call this the front view. Top, front, and side. From this front view, we see that the thickness of the cylinder, the diameter is 0.375 or 3/8 of an inch. So what I'll do is I'll go now to this face, this bottom face of the fork, and I'll create a sketch there. So I have my sketch, it's right over here. And we're going to do something similar to what we did when we made the sliders on that, on the ellipse trammel in CAD 1. I just draw a circle. Right now, it's completely free. And what I need is to put it in the center of this rectangle. So there's,
excuse me,
yes,
but what are the diameters again?
pardon?
The diameters, the length and the size of the thing again. What are they again?
So the diameter is 0.375. Again, these slides
No,
and
for
all
the
the drawings.
small one, like the, for the square, I want to see that one.
I'm not quite sure what you mean, but these drawings and the slides are
No,
on
I
Google
want to go see the
Classroom.
one before. Slide 10. Slide 10. I want to see slide 10.
So these drawings are all in Google Classroom, so you have access to them. You can pull them up on your own screen.
I want to know, like how big and how small the rectangles.
So the dimensions of the rectangles are also in the drawing. We are running out of time, so I think I'll like to focus on getting through this demonstration.
The smaller rectangle.
What we need here is to center the circle in the rectangle here. So a few tools you can use to do that. First of these is that use or project convert tool that we talked about when we were doing the ellipse trammel. You don't have to use this since we conveniently place the origin at the center here. In fact, we could have made this more convenient for ourselves earlier by using a symmetric extrude instead of a directional extrude. But it's good to do it anyway to get some practice. We can make a construction line. So using our line tool, just go from the origin to the top here. Onshape will kind of grab these points for you. So you can see that just by drawing that line, it's completely black just because I used that kind of implied midpoint tool that Onshape does for you. As long as you hover over the right point before you click, it'll be fully defined. So I can take this, make it a construction line. I'll dimension the diameter of the circle, which I know to be 0.375. And I'll center the circle on this construction line, again, using the midpoint constraint. So again, that one works by picking a line, picking a point, and it'll force that point to be the midpoint of that line. So we have this sketch. Next. Yes?
Can I see sketch 1?
Pardon?
I want to see sketch 1.
Here you go, that's sketch 1. Again, like I said, the drawing is on the slides, which is on Classroom, so you can pull those up yourself.
How long is that thing anyway? How long is the rectangle?
It's the dimensions are 2 inches and 1.5 inches.
No, I mean the smaller rectangle.
Oh, that's dimensioned by this offset, right? So all 3 of these lines are just, I didn't really make a rectangle here. I just drew the 3 lines and I made sure they're offset by 1/4 inch in all directions. So there is actually a tool that you can use to do this automatically. It's called the offset tool, but for the sake of time, not explaining a new tool, I just drew 3 lines. If these aren't turning black for you for some reason, it's most likely because you're missing a vertical or horizontal constraint. Although if you are able to dimension it, those constraints probably exist already. All right, so I probably won't be able to get through demonstrating the whole clevis, which is fine. The next step here, as you might guess, is to extrude that circle that we just drew. To know how long that has to be, we go back to the drawing, we take a look, we see that from here, from the base of that fork to the end is 3 inches. So I can specify depth of 3 inches. And that completes the rod of this clevis. And the last thing that I would do is to create these holes, but I'll leave this as an exercise to you just because we don't have a whole lot of time left in the class. The information that you need is all there. The diameter of that hole is 0.25 inches. The location of the hole is 0.375 inches from the edge. So you can use a dimension to create that. And the other fact that you know is that, well, that the center of that circle goes through the center of this fork because the center line goes through that hole. So with that information, you do know that you can, you have all you need because you know how to like create a hole using extrusions.
Excuse me, but like
Yes.
it wouldn't work. Like it would not, because I tried to make, because I can't make that mouth part. It wouldn't work.
All right. We can take a look at that later. For now, it is 9:27. We are getting close to the end, so I'll just have some closing remarks for the class. I do want you to, by next class, create the CAD models for these 3 parts. So finish the clevis, put the hole through it, and also available on Classroom. You can see I posted this material here where you have the drawings for these 3 parts. So you can take your time. All the information is there. It is possible to create these models using these drawings, as I did check that there is enough information. So if you feel like you have to make some kind of assumption, that probably is a correct assumption since the information is there to my knowledge. So everything's in Classroom. Just by next week, when we next meet, in the same document that you're working on this clevis, just create the model for the stand and the bearing cross. And next week we'll assemble it. Here at the end of this slide deck, I did put a few hints about things that you might want to think about when you're modeling these. So for this bearing cross, for example, I'd recommend taking advantage of the symmetric extrude feature. So when you have an extrusion, it is possible to tick this box called symmetric, and that'll make what's this symmetric extrude. So play around with that. That'll make your life a bit easier for the bearing cross. When it comes to the stand, I'd recommend you kind of start out with this top view, making this bracket shape and extruding that, and then creating some holes on these faces. Use the project and convert tool. With that, we are at the end of the class, so
Excuse
I'll take
me.
individual questions. Yes.
Like, how do I get the midpoint thing to work?
So the midpoint constraint works by taking one point and one line. I guess I can show that again. Yep, for next week, just finish up this clevis. So you just need to put that hole through it and then create these models. So the bearing cross and the stand. And the drawings are all on there. If you get stuck, try your best, but we'll see where we are next class.
Excuse me. But can I choose the midpoint of like one sketch?
I'm not really sure what you mean.
Like, can I choose a midpoint of like a sketch? I'm confused.
A sketch wouldn't really have a midpoint, so to speak.
How can I move a sketch?
So there's not really a way to move a sketch. You can change the plane that the sketch is located in, I believe, but
I'm really confused now.
I think what would be best is probably if you showed me what you're referring to.
Okay, but like I can't. My computer recently updated, and now it's not working.
Okay. Unfortunately, I'm not really sure what specifically you're referring to.
Oh, now I can see what I see.
Yeah, I do see.
Okay. Okay, so like I want this to become in the midpoint. See, I don't know. I want to move this.
I'm not sure what point you're trying to make a midpoint.
I want to get this to be right here.
Oh, so unfortunately, that's probably not going to happen because you have these lines that have that point as endpoints. So that constraint isn't going to work the way that I think you want it to. I guess the upside is you don't really need that to be in the center.
But like I can't get the circle to be on the center of like here, can I?
You can, and you can do it the same way that we did that slider in the ellipse trammel in CAD 1. First of all, it seems a bit thick. I think you extruded it to a depth of like 1 inch maybe by default.
Yes, I did. So what's the true exclusion point?
It's 0.5, 1/2.
Yeah.
Yeah. And the way that you'd go about it, create a sketch on that back face. Just click on the back, just click on that face. So X out of right plane. Right now you're trying to sketch on the right plane, which you don't want. Create a sketch using the sketch button, then click on that face that you want to draw it on. So click on that gray rectangle. Click on like the part itself, right, that one. And now you're sketching there. What you can do, try to make a line using the line tool. Yep. We're gonna make our construction line. Yeah. Okay. And so if you hover.
Is this a line, or am I supposed to make something else?
Yeah, hover there, and then just connect it to the other end. Or you could just do that. Do one for the other direction, so it's running side to side. And that'll allow you to obtain the center point of that rectangle.
So I just want to make a circle.
Right. And to constrain the center of that circle, you do need to have that like reference of some kind. You do need some kind of construction geometry in this case.
I can't seem to get this to be like on midpoint.
So right now you can't use the midpoint tool because you have no lines in your sketch, nor any points. What you need to do is start by creating some line. So what I'd suggest is zoom out of it, create that line that goes across from there to the other midpoint, yeah, to there. Do the other one that makes a cross with it. Or actually, you only need one. You're right. So what you do now is you draw your circle off to the side anywhere. Right, and then you can use the midpoint tool where you select the center of that circle and you select that line that you drew. And that's how that works. Now, if you add a dimension to your circle, it'll be fully dimensioned. So it's 0.375, 3/8. And that's that. You can extrude the circle and you're done with that part. You just need to add the holes and you're done with the clevis.
And also I have a question. How can I delete this?
You can make it a construction line, which is, it's not necessary since you can still
I
select the
want to turn
regions.
it into construction line.
Pardon?
How should I like turn this into construction line?
So the tool is kind of in the middle of your toolbar. It's the one next to the project convert
I want to
tool.
like just can I delete this?
You cannot delete it because you have a reference to it.
Can I
So
change
it would break your
construction line?
sketch. Yeah, so you can change it into construction line by using that tool. Yeah, Amy has highlighted it kindly for us. By the way, everyone else, the class is well over. You're free to leave.
Yeah, the rest
And,
of
You want to see my chess set? Alright,
Yeah, sure. Why don't you share that?
why is the circle like? Well, I'm gonna stop sharing. I'm gonna figure it out.
Yeah, sure. Share your chess set, Christopher.
Okay. Let me share.
Also, how much does the thing is?
Very nice.
Yeah, I've
It's-
got a very weird looking bishop. I finished the rook.
Also nice.
Loading student. Looks a bit bad though. The rook is a bit bad.
A matter of taste.
I got the queen right here.
Yep. Also very recognizable.
Excuse me, but I think you make a chessboard.
That's not really CAD.
There you go. The most numerous piece.
I'm missing a knight and a king.
Yeah, the knight will be a real challenge if you feel up to that. I'd recommend trying it. There's tons of knight guides out there since it's a very classic CAD puzzle. Perhaps not the best suited for a program like Onshape, but you could try it.
Excuse me,
Yes.
but what's the length of the
All the dimensions are on the drawings, which are on Google Classroom.
I don't have it.
The Google Classroom should be in that email that you got from Miss He, I believe.
It's I don't have it.
I'll
You need the recording? Steven, you want recording, right?
What?
the code to the Google Classroom is as
Do
follows.
you want the
in
Google
the
Classroom
chat.
code?
Yeah, there you go.
Yeah, why not?
Why didn't you get it? Because we sent it.
Let me go check.
Sure, it's okay. Just get it. Yeah, I will. If you don't have it, I can send you later. And if you don't have questions, we'll maybe let Eugene go. Yeah.
Someone called. What's the name? Because I don't see any CADing or something like that. I don't have it.
The code
So for
is
class, I think we can dismiss. Okay,
as
class
posted.
be dismissed. If you don't have questions, you can leave.